Okay, so now we are on chapter 5. And chapter 5 is going to be exponential functions and logarithms, and we are starting with exponential functions on 5.1.
Your mother was a hamster, and your father smelt of elderberries.
Exponential functions. You have exponential growth, which is some number to an x. So far, you've seen problems that were x to some number. Now you're seeing problems that are some number to an x. Okay, and that is when that number is greater than 1. So like 2 to the x, 5 to the x, 10 to the x. Okay, that's when it's greater than 1. Exponential decay is same setup except it's a fraction. So maybe it's 1/2 to the x, 1/3 to the x, 1/5 to the x, 2/8, 3/7 to the x. Okay, so that's the difference. Exponential growth looks like this. Okay, and what we're saying with exponential growth is it doesn't go by a steady pace. You've been dealing with linear equations, exponential or linear quadratics. Um, those problems go by a certain amount every single time, but not with exponential functions. They don't go up by the same amount every time. It goes up by something different and more severe or more drastic each time, and that's what the exponential growth is. Notice how right here it's barely going up, barely going up. Well, it's starting to pick up pace. Then, holy crap! Okay, it's basically what's happening with an exponential growth. And exponential decay starts off really high and goes down. An example of exponential decay is like the depreciation of your car. As soon as you take it off the lot, if you ever heard that story about how the price of resale value is just, it goes down drastically over time, and then you notice the longer you have the car, it really, after a certain point, it really doesn't matter when you sell it because it's a difference of a couple $100 maybe. But yeah, those are two examples there for you. Example 1, we want to solve this exponential problem. Now the problem is you can't solve an exponential problem unless the bases are the same. This base is a 3, this base is a 9. So how can I make those bases look the same? Well, can you think of a way that I can rewrite the number 9 so that it has a 3 in its base? Yeah, I could rewrite the number 9 as 3 squared. Now the bases would be the same. So I take that 2 and I multiply it by everything up top, and I set it equal to the 3 to the 5x minus 8. Now that the bases are the same, all I have to do is worry about the tops. So really that's my equation here to solve. So I take that 2 through to both, so I end up with a 5x minus 8 equals 2x plus 4. I combine my x's to get 3x minus 8 equals 4. I add 8 to both sides, so I get 3x equals 12. Divide by 3, and I figure out that x equals 4 is my answer. So example 2, let's graph. Once again, so much simpler to graph these on graphing calculators. Okay, so when you're doing this, just graph it on a graphing calculator. The very first one, when you plug it in on your graph, you'll end up getting, if you go to y equals, and you do parentheses 3 divided by 2 end parentheses, how do you get that x up in the air? Well, right under the clear button there's a caret sign, and then you can press your X button, and that will be your graph for that. To find out what your points actually are, if you go to second graph, that will give you your table, and there's the list that I came up with. I just changed them all into fractions is all. Okay, but this is like saying, let's see here, that is your graph for 3 over 2x, and this is your graph for 3 over x. So to plot the points, just so you can see, this is 1.5 and this is 3. So remember that even though this is a fraction, it's a fraction greater than 1. So it's like saying 1.5. So this is negative 2 and almost a half of the way up. This is negative 1 and 0.66666. This is 0, 1. And notice how it's not going up that drastic. 1, 1.5, 2, starting to go up a little higher. So it's a little more gradual. Whereas this one starts off even lower, but it starts going up even faster. So the bigger this number here, the faster it's going to grow. So the bigger the A, the steeper it is. Just something to keep in mind. So take a look at this. We want to graph that. That's a fraction 1 now, so it's actually in between 0 and 1. So when you go and graph that, here's your table. So it's negative 2, 4, negative 1, 2, 0, 1, 1, and then a half, and 2 and a fourth. And there is it. Now notice how this is going down from left to right. Okay, just something else to notice. It's going down from left to right. That's what makes it a decay, that fraction. And the lower the fraction, the steeper it is. So the lower the fraction. So what we're saying is, if I gave you 8/9 x, that's not a low fraction. Okay, a low fraction would be like 1 over 13. The lower the fraction, the more steep is what it's going to be.
Yeah, baby, yeah!
So 3, this is the graph of 3 to the x minus 2 is what we want to graph, and this is 3 to the x minus 2 down below. What's the difference? What happens? What I have here is the graph of 3 to the x. So I just want to show you how we shift them, that's all. Just want to show you how they're being shifted. Okay, so 3 to the x minus 2, what we're saying is, hey, what makes the top 0? 2. So we're going to move all the points to the right 2 because it's a positive 2. So move all the points over 2 is basically what we're doing. So all the points are getting moved over 2, and there they are. But because the minus 2 is on the outside and not by the x, that's telling me whether I move it up or down. And because it's negative 2, I move it down. So every single point gets moved down 2, is what we're saying. So we moved all those points down 2.
Nobody makes me bleed my own blood. Nobody.
All right, and we can hope to try to finish up here in 5.1 when we come back.